Hello everyone, my name is Mei Chen. I'm really grateful for this opportunity to present our work on STPLS3D, a large-scale synthetic and real aerial photogrammetry 3D point cloud dataset. Here are the co-authors. They have my deepest thanks for their contribution and support of this work. Here are the motivations. As you may know, deep learning algorithms are data hungry, especially in the 3D domain. Acquiring and annotating real-world 3D data is a labor-intensive and time-consuming process, and there are issues of long-tail distribution of objects in the real-world training data. For real-world application, there are lack of project-specific objects in the training data. Using military application as an example, there are limited amount of military-related objects such as tanks, fighter aircrafts exist in the training data. So the objective of this research is to investigate the possibility of using synthetic photogrammetric data to augment or even substitute real-world data for training 3D point cloud segmentation algorithms. There has been a lot of work focused on creating LiDAR datasets. In recent years, researchers started to focus on creating aerial photogrammetric datasets. There are also people looked into creating 3D synthetic datasets, but only focused on single objects or ground-level captures with limited 3D environment created by artists. In this work, we proposed a synthetic aerial photogrammetric point clouds generation pipeline. We also released all our generated synthetic data along with 4 real-world datasets that together have a much larger coverage than the existing datasets. Here is our designed pipeline. The input to our pipeline is the GIS data, and the output are the generated synthetic aerial photogrammetric 3D point clouds with annotations. Here is a video illustrating our pipeline, starting with the GIS database. We can download the digital surface model, DSM, building footprints, and road vectors. We then lay out the scene on the 2D plane. We place the light poles, street signs, cars alongside the road or on the road, and also placing other objects procedurally in the scene. After that, we are creating the 3D environments. First, we are creating the 3D building models based on the building footprints and using the CGA scripts. We then place all the game objects in the environment and adding the ground materials, changing object materials to add variations of the dataset. We also use simulation effects such as wind and different sunlight directions. We then use the airsim to simulate a UAV path to collect the 2D images along with the annotation and the depth map. The 2D images is given to the photogrammetric process to reconstruct the 3D point cloud. Here we are using Bentley context capture. Finally, we project all the labels from the 2D space to the 3D point cloud. Here we are showing the synthetic data that we have generated with semantic and instance annotations. You may be wondering, since we can generate the 3D point cloud using depth map or a recasting approach, why do we need to go through the photogrammetric process and generate the 3D point cloud using the rendered images? On the left-hand side, that's a recasted point cloud where you can see a lot of points inside a tree crown. And on the right-hand side, that's a photogrammetric reconstructed point cloud. And you can see that there isn't any points inside the tree crown. Here is a video illustrating the data quality comparison between the synthesized recasted point clouds, synthesized photogrammetric point clouds, and real photogrammetric point clouds. As you can see, our synthetic photogrammetric point clouds is more similar to the real ones compared to the recasted point clouds. This can be better illustrated using the volume density where our synthetic data has a similar distribution compared to the real ones. Based on our designed synthetic data generation pipeline, we have created 3 versions of synthetic datasets. In the first version, we added details for the large objects, creating a large number of forests. In the second version, we added diversity for the terrain shapes and increased the variations of the small objects. In the third version, we added large-size buildings to simulate urban area as well as increasing the variation of the object materials such as ground material pinned on the cars, finishing on buildings. Here are the examples showing our synthetic point clouds. Here are the semantic annotations. And here are the instance annotations. For validation purposes, we also created 4 real-world datasets, including USC, WMSC, Orange County Convention Center, and a residential area. That total covers 1.27 square kilometers. We have collected around 16,000 images using DJI Phantom 4 Pro. The 3D point clouds were reconstructed using Bentley context capture. Here are our real-world point clouds, and those are the associated semantic point labels. To validate our synthetic datasets, we conducted experiments to compare the performance of the synthetic training data and the real-world training data. We used 5 different models for this comparison, including KP-Count, MinowskiNet, RandLA-Net, SCFNet, and Point Transformer. Since our real-world data only contains 6 class labels, we had to merge our synthetic semantic labels to match the real ones. We trained 3 models for each networks. The first one is trained on the real-world datasets. The second one is trained on the synthetic datasets, and the third one is trained on both real and synthetic datasets. No matter where the model were trained, we tested them on the real-world dataset, that is the WMSC dataset. Here are the results. As you can see, our synthetic dataset outperformed the real ones. And when we combine the use of real and synthetic dataset, the networks can achieve their best performance on the MIOU. We then tested the model generalization capability using FDC dataset. Note that the main differences between the FDC and our released real data are that the FDC is located in a cold weather zone, with cold weather tree dominates the vegetation types, and the data were collected in the fall season, so you will see a lot of yellowish trees in the environment. The images were collected with smaller overlaps, resulting in lower quality 3D data. FDC contains various vehicle types, including military vehicles, that do not exist in our released real-world data. Here is a visualization of the FDC dataset, and here are the annotations of this dataset. Here are the results. A similar pattern can be found here, where the synthetic dataset outperformed the real-world dataset, and when using both real and synthetic dataset, the networks can achieve the best performance on MIOU. Since the previous experiment showed that the synthetic data has a very similar characteristics as the real-world data, we also created this instance segmentation benchmark using only the synthetic data. We have provided 2 baseline models here. One is HAIS and the other one is point group. The models were trained using 20 synthetic datasets and tested on 5 synthetic datasets. Here are the baseline performance. Notice that after the paper was submitted, there were more state-of-the-art algorithms that has been proposed, including soft group and mask 3D. They all surpassed our baseline performance here, and if you are interested, you can go to their project page to check out the details. To conclude, we have showed that rendering 3D RGB images and creating the synthetic point clouds from photogrammetric reconstruction is a necessary step to introduce the photogrammetric noises to the synthetic data. Our designed synthetic data generation workflow could be used to generate training data for training 3D segmentation networks and achieve similar performance as if the training data was collected from the real world. The experimental results clearly validate that augmenting synthetic datasets could have a positive impact on the performance of real-world 3D understanding. We released all our synthetic datasets along with 4 real-world datasets. There were over 300 registered users since May 12th. For more details, you can go to our project page at staples3d.com. We also released all our benchmark implementation on our GitHub repo. We also organized the Urban 3D workshop at ECCV this year, and the replay is available on our project page, where you can find the winner talked about their strategies, tricks on doing the segmentation tasks. We also provided the instant segmentation evaluation server on CodaLab. We would like to thank the 2 primary sponsors of this research, U.S. Army Simulation and Training Technology Center and the Office of Naval Research. We would also like to acknowledge the assistance provided by Army Futures Command and Synthetic Training Environment. Thank you very much for your time.